So thank you, Dr. Secondo, for that introduction, and thank you all for staying for the third presentation. So my research is on cyclic voltammetry and metal organic frameworks. And so just to give you kind of a broad overview of what we'll be discussing, so my research was split into two different projects occurring over 2 different semesters. And so in the first semester, I looked at cyclic voltammetry and using that as a technique for analysis in our lab. And in the second semester, I looked at synthesizing a novel metal organic framework. And so we'll go through sort of a background and a results for each of those projects. So to jump into the first semester's work, so the goals for the CV project were threefold. First, to synthesize a metal organic framework that had been previously made in Dr. Secondo's lab by another student. And then to use CV to analyze that MOF to kind of add to the characterization that had already been done on that product. And then third, to optimize that methodology to allow for routine analysis in the research lab for future students, so that other students who make these products can now use this to add to their characterization that had not been previously done before. And so to get into some background, what is CV? So it's a technique for observing the redox behavior of a certain species in solution. And so we do that by applying a range of voltage values to this system. So you can see on the x-axis here, we're scanning through a series of voltage values over time. And you can see that this is linearly proportional to time. We're going from 0.8 to negative 0.2 volts, and then back to 0.8. So we're going through a full cycle there. And in this next diagram, you can see that now the potential axis is the x-axis. You can think of it as a time axis. And as we're scanning through those voltage values, what we're measuring is the current that is produced from applying that voltage. So you can see at the beginning, as we're getting towards a more negative voltage value, we have no current. It's just hovering around 0. And eventually we see a spike in current, and that's the EPC, the peak cathodic current. So this is coming from the reduction reaction occurring from applying that voltage. And then eventually that fades out, and we go into the reverse scan, and in this case we see another peak, the EPA, which is the peak anodic current. So this is the oxidation occurring in the reverse direction, and eventually that fades out and heads back towards 0. And so you can see that we have 2 different reactions occurring here in different directions, and so this is a reversible system. And this is kind of your standard voltammogram you'll see in CV. And so to take these measurements, we use 3 different electrodes. And so we have a working electrode, which is the actual surface on which the reaction is occurring. So this is where the electron exchange is happening between the species in solution and the electrode. And it's where we're applying the voltage. And we have a reference electrode as well, which we use as our standard for referencing all the different voltage values that we are either applying or measuring within this system. And then we have our counter electrode, which is an inner conductive path that allows us to complete the circuit within that electrochemical cell to have that flow of electricity. And so if we jump into what are the applications of CV, so in a more quantitative way, we have some equations here we can use. So we talked about reversibility, right? If we have a peak in the forward direction and a peak in the reverse direction, if we look at the ratio of the peak anodic current and the peak cathodic current, if it's roughly equal to 1, we know it's a fully reversible system because we have that same peak in the top as in the bottom, in the forward scan and the reverse scan. And if it deviates from 1, then we have a bias towards one or the other, and it's less reversible in one direction. And so if you look at the second equation here, we can determine the standard reduction potential, if we run the scan under standard conditions, of the species we're studying. And so we can do that by simply getting the average of those 2 peaks. So when you look in your Gen Chem book and you see those tables in the back, all those different reduction potentials, that's one way we can measure them is using a CV. And so also by looking at those 2 peaks, if we look at the delta between them, the difference between them, we can use that to fairly easily calculate the number of electrons transferred within that process. We can figure out if it's a 1 electron or 2 electron transfer process or whatever it may be. And using this kind of complicated equation here, we can use these parameters in this equation to modify the peak current, the IP here. And so we can use the concentration. So the IP is linearly proportional to concentration, and it's also proportional to the square root of the scan rate. So how fast we scan through those voltage values will change the current that we see. And also it's proportional to the square root of the diffusion coefficient. So based on the solvent it's in or the temperature that we're at will change how that electrolyte diffuses through the solution and thus how reactive it is at the electrode. And we can also change the electrode area itself to change the amount of reactive surface area that we have for that reaction to occur. And so the last application I want to talk about is coupled redox reactions. So when we go through that CV scan and we get to the products, they can actually go on to produce other redox reactions throughout the system because of that voltage we're applying. And so I want to go through an example of that from organic chemistry. So we see this voltammogram here, and we notice we have 4 different peaks present. And so these correspond to 4 different redox reactions occurring within our system. So this is a voltammogram being run on thionine, which is the first molecule we see here. And so peak A has been assigned to the oxidation of thionine to form this cationic species here. And this species can be readily hydrolyzed in water to form tyrosine and benzoquinone. And tyrosine is an amino acid. And each of these products can now act as a reactant in a subsequent reaction going forward. So we can see that tyrosine can be oxidized to form another cationic species, and this has been assigned to peak B in the voltammogram. We can see that benzoquinone can be reduced to form hydroquinone, and this has been assigned to peak C in the voltammogram. And then we can have hydroquinone being oxidized back to benzoquinone. And so there's several different things we can see here in the voltammogram to tell us about this system. First we said we have 4 peaks, so 4 different redox reactions occurring in this coupled system, which is what we see. We can also see that for C and D, they look very much like that first voltammogram we saw, where they have that same general trend. So we could infer that they might be the reverse reactions of each other, that C and D are reversible. And that's exactly what we see, is that benzoquinone being reduced to hydroquinone and the hydroquinone back to benzoquinone is this reversible reaction here. We can also see that we have 3 peaks facing down, right? Which in this case indicates 3 oxidation reactions occurring, while we only have 1 reduction reaction occurring in the top here. And that's exactly what we see as well, that we only have 1 reduction occurring. So CV is a very good initial characterization method to see what sort of reactions occur in solution when we apply a voltage to it and what kind of coupled reactions we have. And so to jump into the work that I did, so the first goal for the CV project was to synthesize a known MOF. And so this was the one we chose. So we started out with a zinc nitrate hexahydrate product with potassium thiocyanate. We just combine those in ethanol at room temperature, and we get a precipitate from that, which is potassium nitrate. However, that's not what we're looking for. That's a byproduct. So we filter that off, and to the resulting filtrate, we add pyrazine, which is our ligand, shown here. And then again, in ethanol at room temperature, another precipitate crashes out, and this time it's our metal organic framework, our product that we want. We can filter that off and dry it. And when we do that, we get 1.76 grams. So it's a fairly high mass, so we have a lot to work with here, and we can recrystallize the product from methanol. And so this is a proton NMR of that pyrazine MOF, our product. And so we see more upfield that we have DMSO, which is our solvent, and we have a little bit of water contamination. And then we have 1 signal coming from our ligand due to 1 chemical environment present in this molecule because of its symmetry. And this matched exactly with what was obtained by the student who previously did this work. I also took an FTIO spectrum. And so what we see here is we have these sp2 carbon to hydrogen bonds up above 3,000 a little bit, which are coming from the pyrazine ligand itself. And then down at about 2050, we have the carbon-nitrogen bond of the thiocyanate. And based on the wave number being about 2050, we can infer that it's N-bonded, meaning that it's actually coordinated to the metal ion through the nitrogen side of the thiocyanate and not through the sulfur side. And again, this matched with what was previously obtained by the student who did this work before. And so at that point, I wanted to try to do CV now. And so before doing CV on the MOF, I wanted to see if I could replicate literature values to know that my setup and my protocol worked properly. And so I chose to use the ferrocyanide and ferricyanide couple, shown here. And this is an often used model system in electrochemistry in general, and particularly in CV. And so the conditions I used were 10 millimolar potassium ferricyanide and 1 molar potassium nitrate, which served as the supporting electrolyte. So that makes the solution in there more conductive so that you can, the reaction can more readily occur at the electrodes. And I used a nitrogen atmosphere, and I scanned from 0.8 to negative 0.12 volts and then back. And then I used a 20 millivolt per second scan rate. And again, these conditions all came from the literature values. I was trying to replicate the results that they already had. And so this is my setup here. So we have a antiquated laptop and software here. This is all this stuff is 10 to 12 years old, so it's very challenging to work with sometimes. And so this is my computer, and then we have 2 different instruments here. The bottom one is a potentiostat. So this instrument can apply and read all the different voltage and current values that we need to conduct these CV measurements. And then the top instrument here is an amplifier. So this allows us to go out to more extreme voltage or current values as we need to. And then we have this black wire coming out here that heads over to the cell and has 5 different leads that we can attach to the cell, to the electrodes there. And so this picture is a closer up version of the cell itself. So we have on the right here our counter electrode going down inside. We have the working electrode in the center and the reference electrode on the left. And then in the back there's a nitrogen inlet, so we can flush the whole cell with nitrogen. And then down here is the cell itself where the solution will be placed, and those electrodes will be immersed in that solution. And so these are pictures of the scans that I took. There's no easy way to export the spectra. And so these are just pictures was the next best option. So as you can see, there's no clear trend. It's not like the ones we saw before. It's not really what we're looking for. There are kind of some patterns there, but it's mostly just gibberish. It's not really anything that we want. There are no clear results. And so there was a lot of troubleshooting. I took a lot of different scans. We'll go through a few of them, but I could show you many dozens of scans, but we won't do that. So I tried putting a new foot on the reference electrode. I noticed the foot was turning blue, and I thought that's not supposed to happen. It's not supposed to be that way, so I thought, why not change it? So I used the Bunsen burner and changed the foot out, and I got no current. There was no response whatsoever. So I don't know why that was, but that did not work. But subsequent scans did give a current using the same reference electrode. So I'm not sure why that was. And so here I tried a higher concentration, thinking my microelectrodes needed more concentration to detect. And I tried it with stirring. And you can see we have some sort of trend going here. It's like superimposed sine and cosine waves. But it's not what we're looking for. It's not what we're supposed to get. So I'm not sure what that's about either. So I tried 10 times concentration again and got like sort of a trend there. It's almost like it wants to. You kind of have that peak coming down there. It's like it wants to come out, but not quite. And then I tried 10 times concentration again without stirring. And I got this scan here, which is much more what it's supposed to look like. We kind of see that peak on the bottom there. The data points are fairly conserved on one single line. So after taking this scan, I mixed up the solution and took another scan, and I got nothing. It was just zero current. So I've never been able to replicate this. It's not consistent at all. I've never gotten another scan like this. I don't know what happened that one day that it worked, but so apparently it does work, sort of, but not consistently. So I tried contacting the instrument manufacturers, and I coordinated with them to get some ideas on things I could do. And I did an external and internal dummy cell test on the instrument, and those all checked out. So hypothetically, the instrument works properly. So I did some other things with them, other ideas they gave me, but nothing seemed to work. And in the end, this was the best scan I got, and it's never happened again. And so this is hypothetically what it should look like. This is what we're desiring to get. So this is a voltammogram from my OEU in the summer of 2016. And so on that OEU, we had synthesized this ruthenium complex here, and then we ran a CV scan on that complex. And so what we see here is you can see this reversible peak here that's coming from the oxidation and reduction of the ruthenium ion itself in the complex. And then we have these three different peaks here coming from the oxidation and reduction of each of these bipyridine moieties within the complex, respectively. And so you can see that all these peaks are readily reversible, and we can see that we definitely have all these structures within our complex, that they're able to be oxidized and reduced. So that's what we were trying to get to, that we could do this on our metal-organic frameworks and get that same kind of characterization. And hopefully someday we still will. So that's the end of the first semester. So then as we went into the second semester, I was thinking, okay, what do I do now? Do I keep going with that project? Do I do something different? And so I was reading in Chemical Engineering News about this new metal-organic framework that had set a record for methane storage. And so the Department of Energy has this target for 263 cubic centimeters of methane stored in 1 cubic centimeter of adsorbent at room temperature and 64 atmospheres. And this new metal-organic framework had almost achieved that at 259 here. And it was 50% higher than its nearest rival. And so that was a very promising result. And they used an MOF with copper nodes connected by 135 benzene tricarboxylate linkers. And this is the paper that I read that in. And so I thought, okay, what if I try to synthesize a metal-organic framework using the same ligand they did, but just switch up the metal ion? So I chose to use zinc because that's the one that's kind of traditionally used in Dr. Secondo's lab. So I thought, okay, I'll try that one and see what happens. And so this is the structure of the metal-organic framework that they used, the one that set the record. And so I want to go into a little bit of background on just what is a MOF. So if you have a metal ion or a cluster of metal ions, it can coordinate to an organic ligand through the heteroatoms in that ligand. And if that ligand coordinates to another metal and another ligand, you can get this framework that can either be a 1D, 2D, or 3D kind of crystalline structure. And so the really neat thing about these structures is that if you look at the structure here, this kind of like general schematic, if you think about these kind of pores or cavities here in that structure, you can fit molecules inside those. You can actually trap molecules in there and bind them in there. And so it has a very high porosity. And because of that, it also has a very high surface area. So if you think about not just the outside surface of the framework, but all the surface area inside, because they can fit inside there, we can have thousands of square meters per gram in these structures, which is really just a staggering number when you think about it. When you think about that much surface area in a few grams of a substance. And the great thing about these structures is that there's so much variability. We can change out the metal ion or the ligand to have different functional groups or different sizes for the ligand. And because of that, we can tailor these MOFs to have certain characteristics that we need. And so to get into that, the applications of MOFs. So we talked about gas storage. You can also have catalysis and sensing and separation and purification. I just want to hit a few key areas of research at the moment. So we can use catalysis, right? They have these metal sites that can act as active metal centers. And so you can think of it like an enzyme, right? In an enzyme, we have an active site that can bind, has a specificity for a certain substrate molecule that it acts on. And in the same way, these pores have a specificity in what molecules they can bind that can then react with those metal ions in either redox reactions or whatever other reactions it may catalyze. And we can do that over other reactions. We can have a specificity for a certain reaction because of that metal center. And so I saw a talk at the ACS conference about using MOFs to purify noble gases. And they were talking about how we can purify radon using this method because we can bind certain noble gases in certain size pores over others, and then remove the one gas and get the other one off the MOF, and we can purify them that way. And so that's a very promising area of research that's going on right now. And so generally, MOFs are not conductive. They don't conduct electricity. However, research is finding now that if we use certain synthetic methods to make them, like using activated carbon, we can actually make MOFs that are conductive, which now opens up kind of this whole new area of research potentially in semiconductors, electronics, and circuits that MOFs can now be used in. So that's a very exciting area of research right now. And so here are some examples of known metal organic frameworks. So this is the one that we actually made, that was previously made in the lab by another student, that we made for the CV, the pyrazine MOF. The student was able to obtain a crystal structure of it. And so if you look at this, we have these square cages here, and they're rather small, they're rather compact, but they can actually, they can trap molecules. And this is, the zinc, thiocyanate, and pyrazine. And if you look at this one here, you'll notice that this one is zinc and 2 amino acids, glycine and serine. And we have these larger cage sizes, right? Now they're rectangular. And we can actually fit 2 different molecules inside there. So again, we're moving up from the pyrazine and getting to kind of a larger pore size. And then if we look at this next one, it gets a lot more complicated just in the sense that there's a lot more in there. There are a lot more different molecules present within that structure. And if you think about it, we have these circular pores here, these circular cages. And they're a different size now. So we have a lot of different specificity and variability within these structures here. So to get into the work that I did, so I used the same ligand, the 1,3,5 benzene tricarboxylic acid, and I wanted to react that with zinc chloride in water. And that ligand is very insoluble in water. So what I did is I did a titration of sorts, and I used sodium hydroxide to deprotonate that ligand. And so as I added the sodium hydroxide gradually, the ligand was deprotonated, became ionic, and went into solution. And eventually all of it dissolved, and I had a clear solution. And then I added the clear solution of zinc chloride and water to it, and I saw an instant white precipitate. There was a lot of it that came out. And so after drying that precipitate and getting the mass, I had about 1.4 grams. This is a very high amount, so I had a lot to work with, which was great. And what I did at first was take a melting point, and the melting point was well above 400 degrees Celsius. So, which is bad on one hand because I can't measure it then, because none of our instruments go that high. So I couldn't actually get a precise melting point. It was good, though, in the sense that my ligand has a melting point of 370 degrees Celsius. And if that ligand does coordinate to form an MOF, the melting point should go up drastically. That's something we'd expect. And even at 400, it showed very little signs of melting. So that was promising, that it had gone up above what the ligand was. So it wasn't just leftover starting material. It was actually a product. So that was promising. So this is a proton NMR of just the straight ligand itself. And so this is in TFA, which we see at 11.5. The reason for that is my precipitate is very insoluble in pretty much every solvent I tried. So even when I heat it up, it doesn't solubilize in anything. And that was a hindrance for a while because I can't do NMR then. But eventually I tried acids and found that it was soluble in acids. And deuterated TFA was one we had readily on hand in the lab, so I decided to use that one. So all the NMRs are in TFA. And so I think this little peak down here, about 2 ppm, is water contamination. And we have one signal coming from our ligand. And again, because of the threefold axis of rotation in our molecule, we have symmetry here. And these protons are all in the same environment. So we'd only expect one signal, a singlet. You'd also expect to see these carboxylic acid protons there. However, this was in a deuterated TFA, which is an acid, so it has functional groups on it like a hydrogen bond. And so I think what's happening is these protons are being exchanged for deuterium. And because it's now deuterium, we don't observe it in the proton NMR because of that exchangeability. And so moving to the proton NMR of my precipitate. So first we see TFA here at about 11.5. This signal is coming from that one hydroxyl group proton there, like what we'd expect to see carboxylic acids, about 11 to 12. And then we see one molecule coming from my ligand in the MOF, hypothetically. And so these NMRs are increasing in concentration as we go up. So I wanted to make sure that this one signal was actually coming from what I was trying to solubilize in the solvent, not from the solvent itself. And so I did that by adding more and more to it each time and taking another NMR to see if the intensity would increase, which it did. We saw the intensity rise, whereas the intensity of the solvent peak stays exactly the same each time, if you look at the actual numbers. And so then I knew for sure that this was coming from my product. And it's a little bit downfield, this signal, as compared to the value in the ligand, which is what we'd expect for a metal-organic framework, that it should be shifted a little bit downfield. So that was also promising that the product was actually, the ligand was coordinated to the metal and not just free ligand. And so here's the structure of our ligand. And again, we have that one chemical environment. And one last thing, it might seem like these peaks are a little bit offset. They're not quite lined up right. I think the reason for that is that in my haste to take these NMRs, I forgot to calibrate some of them to TFA. So that's something I would need to do, is go back and make sure I calibrated all of them so that they're all exactly lined up well. But either way, this gives us the desired information that we're looking for. And so I also did a carbon NMR of the precipitate. And so for those of you in organic chemistry, you may not be used to seeing splitting in the carbon NMR. We don't see that very often because it's carbon and proton decoupled. But we do indeed see two quartets here. And the reason for that is that these are coming from the TFA. So we have these two carbons here, A and B, and they're actually split by the fluorines because the fluorines are NMR active. They have a spin 1/2 nucleus. And so we have three neighbors here. And so we can assign these as A and B respectively based on the size of the splitting that we see. Right? So in this peak, we have a larger J value, a greater coupling with these fluorines. So we can assign it to carbon A because that's the one directly adjacent to the fluorines. And the one at B, which is a little further away, has a lesser coupling, a smaller J value, and thus it's the carbon of the carbonyl. We also see three different peaks here coming from our ligand at these ppm values. And again, based on the symmetry in this molecule, we only have three carbon environments within that molecule. And we can very easily assign those. And so it looks like carbon 3, the carbon of the carbonyl, is down here. This is a very reasonable ppm value for a carbon of a carbonyl. And then for these two signals are two sp2 carbons, right about where we'd expect to see them, 130 to 140. They're on the deshielded side because of two reasons. So we can assign one as the more downfield peak due to the fact that if we draw the resonance structures for this compound, we'll see that these electron withdrawing groups here place positive charges on each of these 1 carbons here. So those 1 carbons will be more deshielded because they have that positive charge directly placed on them. Whereas for carbon 2, it'll be also deshielded, but less so, because in the resonance structures, we'll have the positive charges up on the carbons of the carbonyls. And so they're nearby that structure. They're also deshielded, but they're not directly on it. And so that matched up very well with what we were expecting. And so I also did an FTIO spectrum. This is of just the straight ligand itself. And so what we see is we have that OH stretch up there, that broad peak for the carboxylic acid, about 3,000 or so, a little below it. And then we have 1690, a carbonyl, which is reasonable for a carbonyl that's conjugated with the benzene ring. It'd be a little bit lower. And then our classic carbon-carbon aromatic double bonds at about 1600. And so if we look at the FTIO spectrum of the precipitate itself, the first thing we notice is that it's much simpler. There's a lot less going on here. There's not as much there. And that's promising because in our metal-organic framework, we should have less going on. There's more symmetry there in the repeating pattern, so there are kind of less dipoles available to be IR active. And so what we see is we may have some water contamination up there. The other thing we notice is that our carboxylic acid peak is gone, which is good because hypothetically we deprotonated our ligand, so that peak should be gone. That broad stretch that was there is completely gone. I think this little bit of broadness left is due to water being present in the structure. This was run in water as the solvent for the reaction, so it's reasonable that water molecules are kind of entrained or trapped inside that structure. And so we still see our carbon-carbon double bonds at about 1613. And it also seems like the carbonyl has disappeared. It's gone from its peak at 1690. But it's not gone. It's simply shifted down to a lower wave number, and the intensity is decreased. And the reason for this is that our carboxylate group that's now deprotonated is actually coordinating to the metal. So it's no longer a free carbonyl. So in that case, the wave number gets changed. And so based on literature values for frameworks of this type, we think that 1613 is definitely the symmetric stretch of the carbonyl, that the one at 1357 is the asymmetric stretch. The asymmetric one could also be this peak at 1436 here. it's one or the other. It really doesn't matter which one it is because it's there. It's definitely one of the two, but it could be either one. But either way, this gave us very good indication that our product, our ligand, was actually coordinated to the metal itself. And so elemental analysis. We have requested elemental analysis from IPS, and so far we've obtained carbon and hydrogen back. They have not sent us the other ones yet. We requested oxygen and zinc via ICP, and those will hopefully come back any day now, any time. It's going on 2 weeks now, so I was hoping to get that back before the presentation. So once I do get those, then I can actually work with this data to develop an empirical formula for my compound and actually draw out a hypothetical framework for the structure based on what ratio we have of the ligand to the zinc. And so to go into the conclusions and the future work. So for the CV project, CV is not currently a viable method for analysis. It doesn't work consistently, though it does kind of seem to work maybe sometimes. And so there's several things we could do to try and help that along. So Dr. Secondo and I both agree that getting up-to-date software and a new laptop would be the next step, that the software is very hard to use, it's very antiquated, there's no way to export spectra, there's no way to delete files, it's hard to work with. I would say another good step is to also try a different system. Instead of potassium ferricyanide, try ferrocene. There's a lot of examples out there in the literature of using ferrocene, so it's a very well-characterized compound. And you can use tetrabutammonium hexafluorophosphate salts for that. And we already have these salts. We bought them. So we have them on hand whenever we're ready to do that, whenever the instrumentation is ready. Also, a new reference electrode would be good. The one that we have, the piece at the top broke off. So it still works, but the reactive surface now goes down and touches the frit. So it still should work, but it's not ideal. It would be good to have a new, fresh reference electrode. I would also say trying more concentration values would be a good idea, to go to higher concentrations than I did and also go down to lower values and try to replicate the ones I did and see if you get any results, because that's ultimately where I did get results when I tried a higher concentration, even if it wasn't repeatable. And so for the MOF project, so the initial characterization does give very good indication that we have an actual MOF product and it's what we desire. And so the next step, as challenging as it would be, is to grow a crystal of it, because it's not soluble in anything. So growing a crystal would be challenging, but it'd be a good project to take on, a good challenge. And if we could grow a crystal and send it for crystallographic analysis, that would become the final step in characterization. The other option is to start doing different reactions and varying the stoichiometries that we have. So I use a 1-to-1 molar stoichiometry in my reaction, but you could change that up and use more ligand or more metal ion or whatever it may be, and see if we get the same product or a different result. And then we could also vary the metal ion itself. So I did zinc, but you could try to use cadmium or mercury, kind of the ones traditionally used in Dr. Secondo's lab, or any transition metal ion. We could branch out into whatever it may be. They used copper in theirs, we could use whichever ones and see if we could also make a product. The other idea that I thought of is, once we had this full characterization with the crystallography, is we could actually see if we could find someone to send this product to test it for methane gas storage, to see if it could potentially be used for that. You can press it down into a pellet, and then they can test it with gas storage and under those conditions. That's how they do it. And so that would be something for another student to do. If they got to that point with a product, you could try to do that. I don't know who would do that, but if you contacted someone and they were willing to do it, that would be a great next step. And so acknowledgements, I'd like to thank Dr. Secondo for her constantly patient advice and help, and always being there to support me and guide me and kind of reorient me in the right direction and what I should be doing, and always just giving good advice and always there to support me. I appreciate that. Dr. Greco, who's not here today, but I want to thank him for the great advice he's given over the years, always being willing to answer questions even when he's busy, and just always being there to kind of support me and be a mentor. And I just really appreciate the great advisor that he's been and just how he's helped me through so many different things. And same to Dr. Robertson for just his mentorship and always being willing to answer questions and talk, and just the great times TAing with you and all the fun things we've done. So it's been good. I want to thank all the chemistry faculty. This must be the best department on campus. I'm sure it is. And so I want to thank Dr. Malinelli for always ordering things for me quickly and getting that back so quickly. It's amazing, and telling me many great stories. I really enjoy that. And Dr. Selzer for teaching me many things in PChem that I should have learned in kindergarten, but never did. And so he has kind of brought me up to speed on that, and I really appreciate that. And so I want to thank my fellow young chemists, all you here. You're all a great group of people. And I want to thank Julio for being my lab partner for 2 years over 3 different chemistry courses. I'm sure you're pretty tired of me by now, but thank you. I appreciate that. And just like all of you, Damien, Erica, Jay, you guys are all a great group of people, all of you, and I'm going to miss being here. It's been a really fun 4 years. I want to thank my family and friends. Most of them are not here today, but I would, not be here, not be doing this without them. So I really appreciate the presence and the support and the friendship that they've given. So, and with that, are there any questions? Yes, Jay.
So how common is it to use CV? Because you mentioned literature value. So how common is it to use CV as a standard or a characterization technique in other fields of chemistry other than electrochemistry?
I'd say it's pretty common, especially in materials chemistry. I know it's used fairly often for that, characterizing various different materials. Because if you're looking at using this material for an application in your semiconductors or batteries, whatever it may be, you want to look at what kind of redox behavior it has. So definitely in that field, it'd be very common. And maybe not as much in organic chemistry. I don't know about biochemistry, but definitely in analytical, that would be a common technique as well, too. Does that answer your question?
Yeah.
Okay, cool. Anyone else? Dr. Robertson, yeah.
More of a philosophical. Someone stay away from anything else, the spectra and all of that. There are some freshmen and sophomores in this room, right? So you obviously did a lot of good work. But what is some advice that you would give to some of the sophomores and freshmen that are sitting here and they're going to be doing this research at some point?
Putting me on the spot here. What advice would I give to people doing research? So I'd say don't worry so much about the results you get. Through this whole CV project, I never really got any results. I never got to characterize anything. And we had this whole plan of making different MOFs and doing CV on them and then fluorescence studies. And we had this whole idea worked out that never really panned out because it didn't work. And so even if you don't get the results you're looking for, that's not the point of research. The point is learning as you go. I had a lot of experience troubleshooting CV and doing those tests and things like that, even though I never actually got to do it like I wanted to. And so, but still, it's a good, valuable learning experience. And I guess that's kind of what grad school will be like too, I'd imagine, and what research is like in general. So don't come into it thinking, I'm going to get tons of results, and I'll get all this data, and I'll present it, and it'll be great, and I'll advanced chemistry. It's yeah, that's great, but that's not the ultimate goal because that may not pan out, especially at the undergrad level. So just don't have that as your goal, but have it more as, I'm going to learn a lot and have fun in the lab and get to do some cool things. So I definitely say that. And Dr. Yan.
What kind of electrode you use? What kind of reference you use?
So the counter-electrode.
Did you clean up your time?
So the counter-electrode is platinum, and the working electrode is platinum. And I had the silver chloride as the reference electrode.
Did you always clean your time and then you're working?
Yes, so,
essential.
Yep, no, that's a good point. So they'd been sitting in storage for a while, obviously. This hadn't been used in a long time. And so eventually I polished them. We actually ordered a polishing kit. And I polished them down and cleaned them. And I tried that several different times.
Or pre?
Well, what's the question?
Okay, your electrode is wire or pre?
It's a wire. It's a thick wire, but it's a wire. Yep. It's a wire. So the counter electrode is a wire inside of a glass case that kind of is open on the bottom. And the working electrode has a glass case around the bottom that the wire comes right down into. So it's just a little exposed spot on the bottom. But it is a wire inside of there, yes. Any other questions? All right.